Welcome to this webinar on Introduction to Partial Discharge, Causes, Effects, and Online Detection. Just a couple seconds on EA. EA's been around since the 60s. We were actually part of the national utility when England had one nationalized electric utility. We were their R&D group. And back in the late 70s, they started having failures of equipment, and they didn't know why, and they wanted to come up with ways to test it. And that's where we discovered some of the effects of partial discharge and some of the ways of testing for it non-invasively. So we've been doing partial discharge instruments and testing since the late 70s. My office is in New Jersey, in Denville, which is about 30 miles west of New York City. And from that office, we run all operations in North and South America. The headquarters is in England. That's where they build the products and where they have a lot of the consulting expertise. We have offices in Australia, Singapore, China as well. Hopefully that's the last salesy slide for you. So partial discharge, what is it and why do we care? You know, I didn't know a lot about it until I got into this. It's not something that everybody knows about. It's more esoteric than a lot of the day-to-day tests you do and measures and withstands and so forth. But it is real. I've had a lot of people that have had bad experiences with it. You may run into customers and say, oh, we ran those tests 10 years ago and it didn't work. It didn't show me anything. And that's okay. There's a lot of misinformation out there. And hopefully this will arm you with some good information. And if you ever want to go talk to customers, you want to get us involved in talking to these customers, we'll be glad to help you out. So what is partial discharge? The Wikipedia definition is that it is a failure of part of the insulation to withstand the voltage applied to it. So it's not, the entire insulation not withstanding the voltage would be a flashover, as we're familiar with. But if part of it can't withstand it and the rest of it can still withstand what's left, you get a flash over part of the insulation. And it's an actual spark that you can see. It will occur at the physics, say it can occur at any voltage on any insulation. Practically, we limit it to 3.3 kV or 4160. Below that, it can occur. It's rare because those things tend to have lots of insulation compared to the voltage field applied. And the little bit that might occur is not going to lead to failure in anybody's lifetime. So practical reality is below, pick a number, 2500 volts, 3.3, 4160, somewhere in that range. Below that, it doesn't make sense to do partial discharge. We found lots of failures at 4160, so that's real. And it'll work at any voltage, up higher. It'll work on anywhere you have any kind of insulation. Standard stuff is indoor or outdoor metal clad switch gear, any metal boxes. We might have insulators like a cable termination box on a transformer, in transformers, terminations, any kind of insulation, whether it's air or GIS or oil filled, solid insulation, XLPE, any of those can have partial discharge across it. As I said, if you look at this video, you'll see some real sparks. So if that's happening, you can see it's intermittent, it's coming and going. That's partial discharge. And if you could stick your head in there inside metal clad gear, you would see that. Now that's pretty severe, but I've had customers that couldn't locate the partial discharge to a specific cabinet in a lineup. And so they took the cap off the end of the bus bar section and looked down the bus bar section at night in the dark, and it gets you little blue sparks on all the insulators holding up the bus bar. Now, that's not a very practical way of finding PD, but it is there. So what is partial discharge? This is a good example. It's my one engineering slide. My history, by the way, is 35 years in engineering. And so I like to pretend I'm not a salesman and actually talk something that makes sense to me. So this is the classic example of a capacitor. You have a conductor, you have a ground, and you have some sort of dielectric in between it. That's the definition of a capacitor. Every system you got has some level of capacitance. A cable is going to have a lot of capacitance. Air insulated 500 kV station is going to have very little capacitance. So, and if you've ever done relay settings for a cable, you know that you've got to allow for the charging current. And the charging current is the current that is going through this capacitance in the insulation. So what we can do is we can model any insulation system as a series of parallel and series capacitors. And so what I've got here is 3 capacitors, make my life easy. They're all the same value, and they represent the insulation between the conductor and ground. And as the sine wave is going up and down, and as it's increasing in voltage, at some voltage, the capacitance, it's dividing. So let's say we're at 3 kV, and we've got the same value capacitance, so we've got 1,000 volts on each one of these. C2 is representing a void, a defect, a chip, a crack, dirt, something on or in the insulation that can't withstand the voltage applied. And so what happens is you get to say 3 kV, and let's say C2 can't withstand 1,000 volts. It flashes over, which means it wants to go from 1,000 volts to 0 volts very quickly. Well, in order to do that and still have our 3,000 volts between the conductor and ground, C1 and C3 have to go to 1,500 volts. The only way you can change the voltage across the capacitor is to flow current. And so what partial discharge is an actual current pulse that flows through the insulation, whether it's air or XLPE or whatever, I don't care, but it flows through or on the surface of the insulation from the conductor to ground or from the ground to conductor, depending on the polarity. And that current is the discharge. And so what we're looking for is a way to detect that and determine what we're going to do about it. So that's the science of it. And because it's very small capacitances, it's a very fast pulse, very fast rise time, very short decay. They're typically maybe 5 microseconds long total, 5 to 10 at the outside. And they can be, in the milliamp or microamp ranges. So it's a real low energy event, but it's a real event. And it's unipolar. When you go one polarity, it's one way, and the other polarity, it's the other way. So we break down partial discharge into 4 types, and kind of bounce around here. Corona discharge is what you typically get when you go into a high voltage substation, especially an EHV substation, when you can smell the ozone, you might hear a buzzing. That is where that discharge path, that current path, is actually in the air. So it's going from the conductor through the air to ground. And that usually occurs in situations that are design related or construction related, where you have a sharp edge on the edge of a bus bar or a bolt sticking through, something like that. And right at the edge of that bolt, the air cannot withstand the electric field applied to it. So what happens is that air breaks down, and it's actually a visible spark. It's a lot of ultraviolet energy. There's a little bit of infrared energy because it's got a little bit of heat. But the nice thing with corona discharge is that it's destroying the air molecules. We have lots of replacement air molecules, so they come in, they replace it, they get destroyed, and you have this constant flow of molecules, and it doesn't build up. It doesn't get worse. It doesn't flash over. So we want to not get too excited about corona. The only reason we want to know about corona is so that we don't accidentally tell a customer, you've got surface discharge, which you need to fix, and it's actually corona, and he doesn't need to fix it. He may want to fix it for other reasons, and you might want to tell him it's there, but you want to be able to tell him what kind of discharge he has. Now, surface discharge is the most common. This is where you see the tracking, the treeing, the white powder, the cracking of the surface. All that is where the discharge current is traveling on the surface of the insulation. And that's real common. It's the fastest moving. It is related to the environment, to humidity and pollution and that. Fortunately, it's the easiest to find and the easiest to correct. So that's got good and bad. Internal discharge is where it's occurring entirely inside the insulation. So like that air bubble I showed in the previous picture, or maybe you've got insulation molded around a conductor and it's delaminated somewhere in the middle. Basically anywhere where there isn't access to air. And these are really troublesome because you can look at it, you can inspect it. Let's say you get a contract that maintains a switchgear, and you take it all apart and you clean it and you inspect it and you do a Megger test and you do a withstand test and you put it back in service. It could blow up the next day. And, that's why you need to be able to find internal discharge. Fortunately, internal discharge is more rare. It's more related to manufacturing defects than any kind of the installation or wear or that sort of problem. It also moves the slowest. It grows the slowest. It takes the longest to lead to failure. So we've got a little bit of time. The last is contact discharge, and this is really not partial discharge, but it is a situation where you might have a floating piece of metal in a high voltage field situation. So if I've got some of the things I've seen is where you might have a bracket that's clamping down on a cable. Now the current path is down the cable or down the conductor, but you've got this clamp that's now held in by a rusty bolt. When that bolt gets rusty and then that clamp starts floating, you're going to get discharge from the bolt to the clamp, and that's going to create a very high signature of PD. And the real problem is it's going to interfere with finding other lower level PD. So my favorite one is I had a customer that left a bucket full of tools in the back of a cable compartment and then energized it. And they had these tools in a Home Depot bucket. The metal on the tools made a perfect discharge site, and horrendous amounts of partial discharge registered on our monitor. Fortunately, they were able to de-energize it, took the bucket out, put it back in, and life was good. Now, the guy whose tools they were, he was nice enough to carve his initials into the handles so no one would steal them, and he had a bad day. But fortunately, they were able to find this problem and solve it. So why
does... question.
Yeah.
Is there any type of insulation that's more susceptible to PD than others? Are you going to cover that later, maybe?
Yeah, well, no, I can talk about it now. So, like in cables, the rubber insulations are better than the XLPE. So XLPE and the very old XLPE was real bad. About 25 years ago, they came out with tree resistant. Well, tree resistant is PD resistant, XLPE. The old paper cables, they have a lot of PD, but they can also withstand a lot of PD. They all kind of have different characteristics, some pluses, some minuses, but the most common place we find partial discharge is cable terminations. And that can lead to failure pretty quickly. And that really anywhere where you've got guys out in the field doing work, where they're manipulating stuff, where they're responsible for maintaining the field stresses and that, where, a cable joint, where the guy's got to strip it back, he's got to make sure he gets all the semiconductor off, he's got to not nick the insulation, he's got to put everything in right. That's the most likely. And usually those are done in a trench or God knows where under less than ideal conditions. That's the most likely scenario. And I'll touch on that a little bit more. But there's lots of causes, surface contamination. If you don't clean your insulators, you don't clean your switchgear. We've had I think there's a picture later on where somebody in Florida, out in the swamps, they had an engine test stand, and they had horizontal surfaces between the bus bar, and they didn't go in and clean it. So they got contamination. The contamination attracted moisture. Moisture changed the field stresses and led to discharge. So cleaning your gear is going to help. I talked a little bit about workmanship. That's the number one cause, poor installation. Material defects, sometimes you'll get stuff from a factory that has an air bubble in the insulation or a defect in the cable. It's kind of rare, but it does happen. Improper application, which is also kind of workmanship, you'll see the wrong parts for the job. Anywhere where you've got salt humidity, salt spray, salt fog. We do a lot of work in the Caribbean, and they've got just tons of humidity, and it's salt humidity, and their switchgear lasts about 6 years, believe it or not, before they have to replace it all. And I got some pictures later here. They're at a nonstop battle. So if you guys do any work along the coast, go out to Tybee Island, I imagine they've got bigger problems than you've got in Atlanta, say. So that damage, there's always damage. We see a lot in wind farms. They'll put, wind farms are a pain because they've got a lot of cables. And unlike utilities or big industrials, they are built to last 5 years because that's when the guy who built it's going to sell it. He's going to use the cheapest materials. He's going to use the lowest skilled joiners. He's going to bury the cables direct in the dirt instead of putting a sand bed and all that. we see a lot of wind-form problems. And then age. As things do get old, things dry out and things wear out and plastic gets brittle. So you see stuff in the 30 to 40-year-old range is starting to have PD, even though it may not have had it for any other reason. Like I say, now we see a lot of cables installed in the last 10 to 20 years when they started coming out with cold shrink terminations. And, before cold shrink terminations, you had to be really skilled, and there was an apprenticeship and all this to doing cable terminations. And if you didn't know what you're doing, you didn't try to do it because it was too hard. Cold shrink termination, I can go to Amazon and get a Raychem termination. I did. I got a hunk of cable, I got a Raychem termination, and I did it in my garage. I followed the instructions. Well, the instructions say strip back semicon as usual and clean as you normally would, and things like that. Well, if you don't know what you're doing, my definition of stripping back the insulation is definitely not the same as someone else's. So, the cold shrink terminations, while installed correctly, are as good or better than the hand tape stuff and the hot shrink stuff. But it's allowed people like me to think they can do it, and they can't. So why do we care about partial discharge? When we have discharge, we're talking, millivolts and milliamps and microseconds. It's a very low energy thing in the presence of megawatts. Why do we care? Well, there's a couple of reasons we care. One is heat. So it generates a little bit of heat. It's actually very, very hot because it's plasma. It's a spark. Spark by definition is plasma, which is very hot. But you're not going to typically see it with an IR gun because it's not a lot of energy. So in a very localized area, it's hot, but it doesn't get the whole joint hot or insulator hot. So what happens is that very high temperature is going to damage a little bit of the insulation. And that's going to make the defect worse, which is going to cause more discharge, which is going to cause more heat, which is going to cause a little more insulation to get damaged. And maybe it's just a couple molecules each half cycle, but if you run that for years, you can end up with a really big heat damage type thing. The other problem is gases. So when you have surface discharge, you're in the presence of air. And what happens when you put a spark in air is you ionize the gas, which means to break it down into its component parts. And the oxygen and nitrogen that make up most of the molecules in the air become ozone, which isn't great, but it's not what I'm really worried about, and nitrous oxide. So the nitrogen becomes nitrous oxide. You add a little humidity to nitrous oxide, and you get nitric acid. And nitric acid eats through everything that you use. It'll even eat through glass insulators, given decades and decades. But XLPE, that red panel board, all that stuff loves to eat right through it. And it also leaves a carbon track as the discharge occurs. So the combination of the heat and the nitrous oxide is what's going to make the discharge worse. The worse it is, the more discharge there's going to be, the more byproducts there are going to be, and it tends to snowball. So that's why we always, when we're doing PD testing, we look for trends. How much has it changed from this year to last year? How much is it different from other systems? Because as it gets worse, it tends to ramp up and get much worse. So that's why we care. There's some things we don't really care about. It does create light. And say you were looking at surface discharge on an overhead insulator in a 500 kV substation, you could use something called a corona camera. And a corona camera is basically a UV light camera combined with a visible light camera. And so it's showing you that UV emissions from it. That's good, but you got to have line of sight to it. It creates a fair amount of sound waves. So it creates sound waves that are in the range of human hearing, which is audio, and in the ultrasonic range, which is above the range of human hearing. And so what we want to use is ultrasonic as a detection method. That's why it's got a green circle around here. Turns out that surface discharge generates a lot of ultrasonic energy in a nice tight band that we can find. When it's really, really bad, it creates some in the audio band, and you can actually hear it. When you go into a substation, if you hear partial discharge, it's time to turn around and walk back out. Now, these are acoustic waves. They're purely sound waves. They're traveling through air. They're traveling through solids, through liquids. They're not radio waves, but they're ultrasonic sound waves. So we're going to use that as one of our detection methods. Working to the left here, Radio waves. It's a spark. It creates radio waves. We can use those radio waves to detect discharge. If you're getting radio waves that are occurring at 60 hertz or bursts at 120 hertz, that's a little odd. Why is that happening? So we can use radio waves. They're good in outdoor substations, but they're not so good inside a cable or metal clad switchgear. You basically got a Faraday cage around the discharge site, and so you're not going to get much emission out of it. So it's going to absorb that. So radio isn't so good in your medium voltage applications and your cable applications, but it's pretty good in the EHV type stuff. The last two effects I'm going to talk about are electric. And so the first one is I, or current. That's that current I described. If I can measure that current directly, and that's what you do when you're doing an offline test. When you're doing a VLF test on a cable, you're looking at the current going down the cable from the discharge. Here, we're going to look at it a little differently, but if we can measure that current, then we can certainly see that there's PD going on. The last effect is TEV, or transient earth voltage, and this is probably the least believable thing I'm going to tell you today. There's probably a number of things, but this is the least believable. This is a voltage that appears on the outside of switchgear as a result of discharge inside the switchgear. And there's, outside of the metal clad switchgear is touch safe. You can put your hand up against it, but there's actually minor voltages that occur on that surface as a result of discharge inside. And so we can pick that up from the outside of the gear without opening the door with a TEV detector. And that's what we discovered back in the late 70s and have been perfecting ever since. So those are the side effects, the bad effects, and a couple effects we don't care about. And our instruments are really designed to use all four of these methods to find PD. And the Ultra and the TEV, hence the name of the product, Ultra TEV. So what are these testing methods? We want to be non-invasive. Your customers don't want outages. It's very hard to get an outage. And if they've got a lot of cables or a lot of switchgear, they're not going to give you an outage. But if you could test them all and rule out 95% of them and say, this 5% needs something, then they can focus on that and they can worry about outages, knowing that there's a good reason for the outage, not just a screening test to see if they have a problem. And that also brings you guys in to do the repairs if needed. So ultrasonic and acoustic testing, we're basically listening. We're listening for sound. So we're going to listen through louvers, through the vents, through a contact sensor that actually can hear through the doors, and parabolic dishes, so we can hear stuff going on overhead from a long distance away. And we're listening. So that's clearly non-invasive, right? We're just listening. TEV testing, we're just going to touch the instrument to the outside of the cabinet or to the sheath of the cable, whatever it is, but we're not making any direct connection. So that's non-invasive. Don't need an outage. You can't have an outage. For any of this testing, you can't have an outage. You need to have the system energized. Now, RFCT testing, that's invasive and it's non-invasive. So a radio frequency current transformer, or RFCT, attaches to the cable ground straps. Once that's attached, you can bring it out to a connector and you can go in non-invasively and test that cable anytime you want. Now, putting that RFCT on the ground strap could be considered invasive. Some people do it live wearing an arc flash suit. That's more and more rare every day now. 5 years ago, we'd saw it a lot. But now we see people permanently installing RFCTs into cabinets for customers. And then they come back once a year and do the tests, and they're in the shirt sleeve environment and just connect up. So once the RFCTs are installed, that's non-invasive. And then RF testing, basically you're looking to pick up any kind of signal that might be generated, the EMI that's generated by the PD with a radio receiver. Again, you're listening. And by listening, you're not going to certainly harm anything. So the tests we're doing are clearly non-invasive. They're not going to cause an outage. They're not going to cause anything to fail. You might get some old-time customers that say, I don't want to do PD testing because they did that once and it blew up a cable. And that was back before we understood that you shouldn't do really high voltage tests on cables with DC, with XLPE. And they had a lot of failures on high pot, really. They also have some instances where they'll go to do a VLF offline test and they apply a voltage that's 2 or 3 times the rated voltage or nominal voltage, and it fails. Well, if your cable fails at 2 times nominal voltage, it had a defect. That stuff should work a lot higher than that. So you might end up where you see a failure, customer's going to blame it on your testing, but what happened is your testing really brought out a defect that was there. So you might get some pushback from customers, and you just need to be able to explain that this is not got any chance of hurting your system or causing an outage. Obviously, that's very important to your industrial customers. Okay, so our first method is ultrasonic detection. It's this simple. You're going to carry an instrument, a handheld. There's some various instruments. You're going to wear headphones. You're going to be listening to the sound. So what we do is the ultrasonic energy is above the range of human hearing, and we use a technique called super heterodyning to bring it down into the range of human hearing without changing the characteristics. So we take it from 40 kilohertz and we bring it down to 2 kilohertz, and you can hear it. It sounds like you would expect it to sound. It sounds like arcing, sparking, a lot of buzzing at the peaks of the voltage. So that's one thing you're going to do. And you've got this airborne or air-based microphone, and you're going to try and find an air path from the source to the sensor. You know, lots of switchgear has vents, louvers, gaps around the doors. Sometimes these doors don't fit very well. Some way in. You don't need a direct line of sight, but you do need an air path between the source and the sensor. Just like if you were listening to me, you need to have an air path from my mouth, which is generating the signal, to your ears, which are listening for it. If you've got something that's very sealed up tight, we've got a contact sensor that you can put on the door, and it'll listen on the other side of the door. Basically, you take the instrument, you move it around each panel. If you find something, you record it and move on to the next panel. It takes a minute or so at each panel to go through and do the test. It actually takes more time to print out the report and format the report than it does to do the test. You can get in and out of there pretty quickly. So that's an ultrasonic test. We are really worried about temperature and humidity when we do these tests, because humidity plays a big part on whether the discharge is occurring. When it's very dry, the discharge can actually stop, and when it's very humid, it gets worse. So we want to record that so that if I do a test this year, and James, you do a test next year, and we want to trend it, we want to look over time, and I did the test, it was 90% humidity, you did the test, it was 15% humidity, the results are not going to correspond. So we want to take that. Our instruments have built-in temperature and humidity sensors, and that's included in the report, so you can get that. Discharge has a very distinctive sound. It can come and go in stages. In the early stages, the more steady it is, the more severe it is. And the last is the biggest bad news of today's presentation, is the severity is not necessarily related to the amplitude you're measuring on the instrument. So the instrument's going to give you a number, but because it's sound, if I put my hand in front of my mouth, the level goes down, but that doesn't mean the discharge went down. So what you need to do is take the numbers with a grain of salt, and if they get worse over time, or you have a number of identical cabinets and some are bad and some are good, that tells you something. So you need to look more for the trends or comparisons to other equipment than the actual number. Now, if the actual number is really high, it's pretty obvious. I'm talking about borderline cases. Our instrument uses 6 dB as the transition point from where we say green to red. That doesn't mean that if it's 8, you need to panic, and if it's 5, you're fine. What it means is if it's 30, you got a real problem. If it's real borderline, you need to kind of watch it over time, sort of thing, or watch it over humidity. So I don't know if you guys hear that sound, but that's the actual discharge recorded. Got a lot of 120 hertz component to it. So what it is at each voltage peak on the sine wave, which occurs 120 times a second, is a burst of 40 kilohertz noise, and that's what we're picking up, and then we're converting it down to 2 kilohertz center frequency so we can hear it. And that's really good because your ears are the most finely tuned instrument. You can listen to a singer sing the same song in concert and in the studio, and you can tell the difference. your ears are incredibly fine-tuned instruments. And so that's one of the three primary methods we're going to use to determine the difference between noise and real discharge. So another thing, I mentioned humidity, and I already talked about this a little bit. This is an actual graph from one of our monitoring systems. We have handhelds, incident survey type instruments, and we have 24/7 monitors you can install. This is from a customer, and you can see where the relative humidity spiked, and the blue is the ultrasonic level spiked at the same time. That's always a good indication. Other noises like transformer hum or a loose panel that's vibrating and creating ultrasonic noise, that's not going to change with relative humidity, but partial discharge does. So if you're tracking something and you see spikes in the ultrasonic activity and they relate exactly to the ultrasonic, to the relative humidity, then you know you've probably got partial discharge. So that's a really helpful tool. So I said the numbers aren't 100% worthwhile, but everybody likes numbers and customers want to see numbers. So, and they do help to some extent. So if you're way up there, and this is a logarithmic scale, so from 0 to 10 is an increase of 10 times, from 10 to 20 is an increase of 10 times, from 20 to 30 is an increase of 10 times. So 30 is 1,000 times louder than 0. So here 20 is pretty loud. If you're getting 20, it doesn't matter. You don't need to trend it. You don't need to worry about it. If you hear the sound, look at some of the screens and determine, yes, it's really PD and it's 20 dB, you need to take action immediately. If you're in this anywhere from, say, 15 to 7, then it might depend on what kind of trends you're seeing. If it's real low, even though you might think you hear something, below 6, don't get too excited. So there are some numbers. They're not absolute numbers. Everything's a little fuzzy in the world of PD, but there's some numbers for you. So TEV, like I said, this is the most unbelievable thing I'm going to talk about today. If we have some high voltage component inside a grounded metal box, and it's held off the inside of that box by some sort of insulation, obviously I've drawn this really simply, and I have a discharge site. Remember my 3 capacitors. If I have a discharge site in the insulator and I get a current, it's going to flow through that insulator to the inside wall of the box. And that box could be switchgear, it could be bus compartment, it could be unibus, it could be shielded cable. I don't care. But what happens is it won't go through the metal. At these frequencies, it's such a narrow pulse, it has to have the free electrons that are on the surface of the metal to travel. So it travels on the surface, inside the surface of the switchgear, until it finds a way out. And our switchgear is not sealed, welded shut. So there's joints, gasket, bolt holes, things like that. It finds its way to the outside of the gear. It then travels all over the gear looking for a path to ground, and your gear is grounded, so it does find that path. But this ground, which is very, very low impedance at 60 hertz, is very high impedance at, say, 60 megahertz. It's inductive. It's not finely braided cable like you would see at a cell phone power installation. It's big, thick bus bar that can handle tens of thousands of amps. That doesn't have a lot of surface area, so it's not a good ground. So if we go back to Ohm's law and we say I've got a current flowing across an impedance, I have a voltage. And so it's an actual voltage you can measure. And so you have some sort of probe, and the probe is basically a voltmeter. The first lead is a capacitive plate that's built into the front of the equipment. And the second lead is the conductive body of the gear, which you hold in your hand, sort of like holding an AM radio. You get better reception when you hold it. You put it down, the signal goes down. For those of us old enough to remember handheld AM radios, basically it's a voltmeter, and we're just measuring that voltage. And so if we can measure that, it's very narrow. It's a couple microseconds. It's small. It might be 100 millivolts. But I can measure that voltage, and I can see something going on inside, even inside the insulation itself, inside the switchgear, and determine that there's an issue going on. So that's how TEV works. It's a bit unbelievable, but it really is there. We've proven it over the last 40 years. If you're doing any outside work where you have an insulator and that insulator is grounded, a metal pole or a ground wire, maybe coming off a Viper sectionalizer or something like that, you can put the sensor right on that wire going down the pole, or put it on the pole itself. There's going to be an impedance between that pole and ground, and you can see the voltage that is on the actual ground wire. So you can use it for overhead stuff. We like to look at two numbers when we're talking about TEV, because remember, this is a really small signal we're trying to pick out of a really big background voltage and high noise, so it's not trivial. We're going to look at two numbers. One is the actual TEV reading on a logarithmic scale. Like I said, 0 is equal to 1 millivolt, 20 is equal to 10 millivolts, 40 is equal to 100 millivolts, and 60 would actually be equal to 1 volt. What you've got is you've got this reading, and this is microvolts, I'm sorry, so 60 would be a volt. Like I say, that's not 1,000 volts. And then the other thing is the pulses per cycle. If you think of discharge occurring at the voltage peaks, and you got 2 peaks in the cycle, that's 2 pulses per cycle. Maybe your discharge is bad enough that you can charge, discharge, and charge again in the half cycle. Now I'm at 4 pulses per cycle. So the number of pulses per cycle gives you some indication of the severity. It also gives you some indication of where it's occurring. A little air bubble inside insulation, it's not easy to have that charge and discharge and charge and discharge too many times in a half cycle. So once you get above 5 or 6 pulses per cycle, it's hard to see that internal as doing it. But if you think about surface discharge, where it's that tracking and treeing with all those different branches, and they all fire at slightly different voltages, you know, you 6 to 20, 30, 50 pulses per cycle is possibly surface discharge. A lot higher than that is going to be some probably radio waves or some sort of electronic interference, and very high levels of discharge are where you've got bad contacts, you've got floating metal, that sort of thing that I've talked about before. Little quick summary. Internal PD, not affected by humidity. A lot of this is common sense. Just know, you may not have spent the time to think it through. There's no air, so there's no humidity effect by humidity. It's lower pulse counts. It's a lot harder to hear, and TEV is going to be your best bet to detect it. External PD is very much humidity related. Higher pulse counts, sometimes audible, definitely audible in the ultrasonic band, and you want to use ultrasonic to test for that. Now, we don't know what we're looking for, so we want to do both tests every time. And fortunately, the instrument does both tests, so you can go through and do a complete rack of gear without too much trouble. The last thing I want to touch on is cables, and I hit that up a little bit in the beginning, but cables are designed that inside the cable, the reason the cables are shielded is so that we have a nice controlled field. You've got the conductor, then you've got the semicon layer to smooth out the field, then you've got the insulator, then you've got another semicon layer to smooth out the effect of the shield. And between there, you've got a nice flat distribution of equipotential lines or field lines. When we cut that shield off, all bets are off. And so we need to put something in the end of that cable to gradually reduce the field strength to where air can handle it. If you don't, you're going to get discharge. And this is the most common thing. Mistakes made in any kind of construction at the end of the termination are going to give you discharge. So if you think about it, I've got a voltage starts at 0, goes up to something, and I've got these field lines that are nice and evenly dispersed through the insulation. That's great. Now, if I have some sort of defect, those are going to be concentrated around that defect, and obviously that's going to be a lot higher voltage problem, and it's going to lead to discharge. Here's a classic example. I love this picture. My favorite picture out of all of them. If you're cable joiners at all, and you see this semicon layer, and you see this cutback, you guys having a bad day, this sharp corner caused a concentration of electric field. That caused discharge. The discharge traveled up the XLPE, ate through it. You can see where it's actually eaten through. That's from the heat of the spark eating through it. Also, notice that this is carbonized. It leaves a carbon track so that I now have the effect of voltage in places that I didn't plan. If you see tracking on the inside of an insulator, I now have voltage at the end of those PD tracks which could lead me closer to arc flash, right? If I've got voltage where I shouldn't, and then I move something, I could end up with arc flash. Fortunately, with cables, they're hard to see. They're buried in the ground. They're up in racks. They're God knows where. And the discharge can be occurring anywhere. It tends to occur at splices and terminations. But if it occurs in the middle of the cable, it still has to travel. That current pulse has to travel somewhere. And it travels down the shield until eventually it finds a ground strap. If you're grounded on both ends, it'll divide and go between both of them. But if we put something around that ground strap called an RFCT that can measure the electrons going down that strap, I can create a picture that looks like this. That is my pulse and maybe even my reflected pulse. This is no different than a VLF test, but it allows us to do this test and get the discharge in a specific number without connecting to the cable, connecting to the high voltage. So I can safely connect to the ground strap and take a measurement. So that's PD in 45 minutes or less. And now I'll hit up on how we measure it. So this is our instrument called the UltraTough Plus 2. The guys in the Chesapeake region and the guys in Raleigh have a couple of these each. It's our #1 selling product. It's designed to do all the tests that you need and survey spot check type mode. It's got a built-in ultrasonic tester, and it's got plug-in sensors for TEV and RFCT and temperature and humidity. It's all touchscreen based. It's our 4th generation product. We are a service company in the UK, and we use our own products. And so we make changes that service guys want. I think you'll see that when you use it, that it's got a lot of things you'd like. One is PD classification. It's going to help you determine what's noise and what's real PD. So it's actually going to give you hints as to what it thinks PD is. It's got built-in storage. It's going to record data. It's going to generate reports. It's got a built-in web server. There's no extra software to buy. There's no extra software to learn. Once you use this instrument, you can take it to any machine, connect to it via Wi-Fi, and connect to the website and see the graphs and charts and that. So the instrument itself has a built-in ultrasonic sensor in the front of the unit. It has a built-in TEV sensor in the front of the unit. It has a variety of ports to plug in additional sensors. It's got a SD card slot where all the data is stored, so you can just pop that out, store it, put it in the laptop. Like I said, it's got built-in Wi-Fi. It's also got a USB connector. You can connect it to your laptop. I'm not going to go into the product in huge depth, but it's pretty well done. Like I said, it's our 4th generation. It's all touch screen. It's going to give you, nice indications of what test you want to run. Just click the button. There are very few settings in the gear, and that's intentional. The settings are related to Wi-Fi, and do you like this? Hear beeps when you push the buttons, or you know beeps, or things like that. But in terms of measurement settings, there's virtually no settings. There's only one setting in the whole box that can change the reading, and that's so that when James does a test, and a year later I go out and I do a test, we got results that we can compare. If it's a really complicated box that I can change a dozen settings on and get totally different readings, and I take readings over 5 years and I've changed the settings each year, I can't compare them. So we intentionally limit the settings. If you plug in a sensor, it automatically detects that's the sensor you're using and puts that in a report that I'm using this sensor in the report. You don't have to change, set it, I'm going to do this, I've connected this, I want to use this sensor. It automatically detects what you plugged in. The system is going to give you indications of what's going on beyond just numbers and graphs and so forth to try and make it easier for you. Here we've got a TEV screen. I've got a nice big number, 29 dB. That's pretty high. But my pulse per cycle count is 28, well above the 5 or 6 that you might see with internal discharge. So it's going to tell you that it's probably surface discharge and that you need to check ultrasonics, because ultrasonic is the best test for surface discharge. So it's going to help you, guide you along. If it was internal, it would say that possible internal or possible high-level internal. The numbers change colors from red to green to give you a better indication. A lot of little tricks to tell you what's going on. You can see the temperature and humidity readings up on the screen. This screen here is the ultrasonic measurement screen. Gives you a number, and there's an advanced algorithm that we've built that says either PD or noise. That's it. And that is not 100%. There's no one thing that's 100%, but it's pretty good. I'm trying to build a simulator here, and I haven't been able to fake it out yet. So you've got that. You've got the sound that you're listening to in your ears, and you've got this guy below, which I'm going to talk about in the next slide, called a phase resolve plot. So you got 3 different methods of interpreting ultrasonic data, and 2 out of 3 leads me to believe it may be PD, and 1 out of 3 that part may be getting fooled by something's going on, but you're not going to get all 3 of them to be wrong. So 3 out of 3 is a slam dunk. 2 out of 3, maybe I need to look a little closer. 1 out of 3, I need to make sure that probably nothing's going on, but I need to try and confirm that. So it's always good when you've got a way to triangulate in on the real answer. So phase resolve plot is a great tool. It exists in offline tests. If you guys have used offline test equipment, partial discharge tends to occur at the voltage peaks, just before the voltage peaks. But you notice they're 180 degrees apart. Now, we are not aligned when we're taking a measurement. We're not aligned to the actual voltage because we're not attached to the voltage. And plus, you've got 3 different phases. So what we're going to do is say, are we seeing something half a cycle apart? Are we seeing 2 groupings of energies? And so this screen is our phase resolve plot. Each dot represents at least 1 event that we captured. So all these little green dots mean I captured one event at that relative phase and that amplitude. As I get more and more dots that overlap, I change the colors to make them darker, blue, red, so forth. And so I can see on this slide that I've got 2 groupings of energy at a higher level, maybe 20 dB or maybe a little bit higher, half a screen apart. That's a good indication that something's happening. Now, if I have ultrasonic energy, it is synchronous with the 60 hertz, and it's occurring at twice a cycle. There aren't a lot of other things that are going to do that other than partial discharge. So that's a really good indication. Plus, I've got the algorithm. Plus, I've got what I'm hearing in my ears. So all those are going to help combine to let you find out what's PD and what's noise. I talked about the temperature and humidity probe a little bit. I'm not going to spend a lot of time on that. You plug it in, and it's just going to read the temperature and humidity and automatically put it on the screen and automatically store it with the results. So if you're going to take TEV measurements, it's as simple as this. The guy's holding the instrument flush up against the switchgear, the panel, or the door. What I typically do is hit 2 or 3 spots on the door just to see that it's the same. And I can record it, I can save it, I can take a screenshot of it. However I want to record that information, I can. Maybe I'm just going to look at it and move on. We've got a variety of different screens that help you. This is one of them. So this is the interpretation mode. The interpretation screen is going to have your values up here. It's going to have all the same information on the top. And it's got the bar chart to make it a little easier to visualize. But then it's going to tell you, okay, here I've got 32 dB, I've got around 1 pulse per cycle. That's an indication of internal discharge. It's not 100% certain, but that's gives you an indication of where to go. Here I've got 85 pulses per cycle. That's pretty darn high. That's probably noise. So I'm not going to get too excited about this number until I figure out what's going on. And this is a good screen to start. Once I get past that, there's the phase resolve plot is also very important in TEV. So I want to look and see. Here I've got some green dots that are kind of spread randomly. It's probably noise. We'll look at my pulse per cycle count. It's not even a half a pulse per cycle. So if it's occurring very, very rarely. So that tells me I don't need to get too excited about this. Another screen that we give you is a bar chart. What happens is every 2 seconds it displays the peak reading. And so if you've got something that's all over the place, it can show you that it's varying wildly. Typically, it's used just to kind of a training screen to get you some idea of how long it takes to settle out. It only takes a couple seconds to typically settle out. This doesn't tell you a lot more information except whether it's steady or if it's varying a lot. we actually capture waveforms in real time. So every 2 seconds, we're going to grab a waveform and put it on the waveform screen. And so you can see this is way too narrow for a normal TEV. You can zoom in on these. You can save them. If you capture something for the survey, for the report, it's going to capture 10 waveforms that you can look at individually on your PC. Gives you a really good indication of what you're looking at. The last screen you have on TEV is called a histogram, and that is a screen that gives you the amplitude in dB versus the number of times it measured that amplitude. So what it does is it gives you groupings of where things might occur. And this kind of grouping here, while it's still in the green, it's pretty low level, it's kind of the shape we see with TEV. If I saw a big wide spread of values that were kind of random, that's not TEV. If I saw a single vertical line, which says the amplitude is exactly always the same amount, that's not TEV either. That's something electronic. So it really helps me grasp what's there and what's not. The fact that it's showing it all will also let me know that if I had a high level source up here, I would also be able to see a low level source. So it prevents high noise from hiding low signal. Ultrasonic is a lot simpler. You've got a variety of sensors you can use. You've got the built-in sensor. You've got a flexible sensor, so if you're holding the instrument in front of your face, you can take that sensor and move it around the door, move it around the gaps while still being able to read the equipment. The parabolic dish is great for looking at stuff on the ground. It's at about 30 feet. It's got about a 1 foot spot, so you can use it and work it up and down insulators or cable terminations on a riser pole, that sort of thing, and look for PD without getting in a bucket truck. And the last thing is the contact sensor, which is going to allow you to, let's say we've got switchgear that's indoor-outdoor stuff. The outdoor is the cable compartment. It's got no louvers. It's got weather stripping. It's all tightly sealed. I can slap that on the outside of the door, and it's going to tell me what's going on inside. Now, unfortunately, it's totally non-directional. If I've got noise outside, it's also going to pick that up. So it's the sensor of last resort, but it does work when you've got sealed compartments. So here's an example. If I've got louvers or something, I'm going to try and get that air path from the source to the sensor. If I've got no louvers, I'm going to use this contact sensor, and what it's going to do is it's going to turn this entire panel into a sensor. So that's kind of the idea there. So this is the ultrasonic screen. I touched on that a little bit. I've got my algorithm, I've got my reading, and I've got my phase resolve plot. That's it, just one screen. It's all there. Plus, I'm listening with the headphones at the same time. Here's an example of the algorithm. It's showing us noise. And if you look at this phase resolve plot, well, sure, there's no relation to the 60 hertz there. That noise is, all those events are purely random. And if I were to listen to the audio, I can tell you right now that would not sound anything like this one on the right. Huge number, 1,000 times stronger than this number. This one I'm very much concerned about. This one I'm not concerned at all about. So that's how the instrument is going to try and help you make these determinations. A generation before, all you had was the headphones, and a lot of equipment, all you had was the headphones. So here's some real examples of PD. So here are the boots were too close up in the termination. This is the unshielded portion of the cable, and you've got this white powder. You've got a phase resolve plot, which is clearly two groupings, half a cycle apart. The peaks are much higher than the noise floor. The noise floor looks like it's down around 5 dB, and the peaks are over 30. That is classic PD. If I put this in here, classic PD, easy to find, and this was found from outside the cabinet. Now here, so I talked about corona briefly, and when you have corona discharge, it also generates a lot of ultrasonic energy, but it tends to be one polarity to the other. It doesn't occur the same amplitude on the positive and negative. And so what happens is, if you look at these charts, there is going to be much more in one grouping than the other grouping half a cycle apart. So here we have this one grouping which is nice and high, and then the second one, which looks like it occurs right here, is really low or non-existent at all. I can determine very easily that that is corona. And here, there was actually corona and PD occurring. So there was PD occurring there, but there was a corona coming off these bolts. And so that's how you can tell if you're looking at overhead insulators, overhead switch gear, and buses and so forth. If you see one hump, you're listening to corona. And it's going to have a much lower sound. It's going to have a lot more 60 hertz because I don't have 2 pulses per cycle. I have 1. So it's going to sound like this. So you see, that sounds a lot more like 60 hertz. With a little bit of experience, you tend to learn these sounds, but from the phase result plot, it's pretty obvious. So here's an example of just noise. Yes, there's some phase result plot. It's occurring 6 times a cycle. You know, that's something mechanical going on, not PD. And here's just purely random noise. Look at this phase result plot. Huge levels, but just, you know, incredibly loud noise. Now, this may prevent us, and let me just play this real quick. If you were listening to that, it would be pretty obvious that's not PD. Now, the concern is that it's so loud that I might not hear PD occurring underneath it. You might see it in the phase result plot, but you certainly never hear it. This screen, by the way, is the output of the report. So when after you've taken the data, you download it to a laptop and you open it up and you get this sort of information. So this is on one specific test. It tells me that I used a flexible microphone. It tells me the algorithm thinks it's noise. It tells me the algorithm is 100%, so it gives you a classification certainty. The algorithm is 100% certain. You may not be, but it is. And so this is the kind of information you get out of the report. Here's an example. I did this myself. This is on the roof of a freeze-dried food building where they require factory guys to come do a test. And every year we come and do a cable test on all the 13 kV cables. I went up to this cabinet, and it's dead front. It's safe to open the door. I'm a bit of a chicken, though, so I do an ultrasonic test around each door and a TEV test on the door before I open it because I'm worried about personal safety. And on this particular case, we noticed a fair ultrasonic signature coming out of the gaps around the door. So they got somebody to wear an arc flash suit and open the door, and I stood back at 20, 30 feet and used the parabolic dish. And I just ran it up and down each one of these elbows until I found the highest level. And if you look in this spot here, you can see that red dot. The ultrasonic dish actually has a laser sight on it, and that dot is from the laser. And if you look around the bushing, you can see a little bit of white powder. If you look at this bushing here, there's no white powder. So what had happened is the cable termination guy he was a little bit short when he made the termination, put the elbow on, but he had a crowbar so he could make it fit. And he pried this thing on, he bent the bushing, and he had a big gap in the rubber boot. And when they pulled this off, the whole inside was covered with this white powder. They re-terminated the cable, cleaned up the bushing. They didn't replace the bushing, they actually cleaned up the bushing. Came back a year later, and it was perfectly clean. That would have led to a failure, which would have taken out one of their main refrigeration units. So that's a use of the dish, even though you're not necessarily looking at outdoor overhead gear. Ultrasonic measurements, you're going to wear the headphones, you're going to use whatever sensor is appropriate, and you're just going to move around slowly, trying to get an air path from the source to the sensor. And then you can save it, you can do a screenshot, you can record it. The instrument actually records 10-second audio clips, so you can listen to it, you can email it. It's got a Wi-Fi hotspot built into it, so you can send the audio clip to your laptop or to your phone and then email it to somebody. So if one of you is out in the field and one of you is an expert, you can shoot them that email and say, hey, does this sound like PD to you? You can send it to me, and I'll give you an opinion. So it helps you interact, helps you work as a team on these until you become very conversant in it. When you're doing cable measurements, I said you're putting the RFCT, and I think I got a better picture of the RFCT. So that's what the one that comes with the unit is. It's a split core clamp-on RFCT. The problem is that's got to go on the cable ground, which isn't always accessible, certainly in metal clad switchgear. in outdoor substations or riser poles, you can clamp it on the ground strap on a riser pole pretty easily. If you're going to do a lot of stuff for a customer, you might want to try and convince the customer to buy and install these RCTs ahead of time so that you can come in and do this test whenever. But it's as simple as plugging it in, and then you get most of the same screens that you would with the TEV test. You get the waveforms, you get the this reading screen, you get the phase result plot. Nice thing is you get a real reading in picocoulombs. We're measuring the number of electrons that go through the center of that RCT, so we can give you an absolute number here. Here's an example of, the good old days where they would just put on their arc flash suits and jump in there and put the RCTs on. We have a hot stick mounted RCT that's a shotgun Hastings hot stick with a new end that we designed that allows you to clamp it on from a distance. It's not perfect because you still have a cable coming off there. It's not really live line work, but at least you're not sticking your head and shoulders inside that cabinet to take the test. When you're all done, you can just take readings as you go, or you can set up a test in advance, or you can record stuff as you're going, and then you connect to the instrument via Wi-Fi or USB or whatever, and it's going to show you all the results that are stored. You can download them, you can view them. You can create a workflow, which is a set of tests. Let's say you do the survey one year and you know you're going to do it next year. You can click this, and then it's going to load all those tests into the unit, so you can follow that next year and make sure you did the exact same test that you did this year. If you've got guys in the office, they can create workflows using Excel and download them to the instrument for the guys to use out in the field. The reports actually look like this. They're made to look like a set of metal-clad switch gears. If you looked at it from above and split it, so this side is your cable compartments, down here is your breaker compartments, and the middle is your various chambers and your bus bars and so forth. Anywhere you take a test, it's going to change color. It's going to be red, green. This is an older version of software. It's going to be red, green, or yellow based on the highest reading. May not mean it's PD, but it gives you some indication of where things are red or green. And it's also, by giving you a physical representation, it lets you see that maybe I've got these two cabinets or these three cabinets are all in the red. There is some bleed from cabinet to cabinet. It gives you some indication something's really going on here. Inside these, each one of these little boxes, there's some number of icons that indicate the number of tests or the individual tests that you've done. An icon is TEV, cable, or ultrasonic. You click on that, and then you get a screen like this. It gives you the information about the actual panel that you're at. You can do the phase result plot, the histogram, the waveforms, all that's available. And this is all web driven. There's no software running on the PC. You can read it directly from the instrument. You can store it and then open it on your laptop. You can attach it to reports. You can cut and paste these pictures out and put them in reports for the customer. Try and make it easier. You can download all the data as raw data in CSV file format if you want to manipulate it more. We've got a couple customers that have big PD programs that are working with the raw data themselves. Now, all this equipment, all this data that you loaded in here, that can be preloaded into the instrument as a workflow. And what you can do is the instrument itself, the last feature I haven't talked about is it's got a reader for NFC tags. So these are little adhesive tags. You get them printed up and say ABM on them, and you stick one on each piece of gear that you test. And then the instrument, the first time you do a survey, you go through and you write the panel number to that tag, and it's got a memory chip in there, and it'll store that forever. Next time you come and do the test, you just hold the instrument up to that, and it'll say, okay, I'm at panel 706. Great. And it'll let you pull up that data from the workflow without doing all this typing at every station. So it makes you faster, more efficient, less errors, and less time wasted standing in the middle of the substation. So these are the different screens. Here's a waveform screen showing a typical TEV type waveform. You can show them all at once. You can show individual things. You can download these to Excel. So I just want to show you a couple examples. And that's the end of my presentation, but some of the things we found. So here, I have no idea why there's only two, but there's two phases going up through this, whatever it is. I've never seen anything like this. If I have two phases that are side by side without any shield between them, they're going to discharge. And you see this white powder, you see this degradation starting. we detected this from outside using ultrasonic. Here they've just used these boots that are the wrong for this spacing. And so where I've got these two circles touching, I've got a high concentration of field, I've got the white powder, I've got the tracking. I can also see that I've got a lot of rusting in that. When you have nitrous oxide inside that cabinet, there was no evidence of water. You can see the bottom is dry as a bone. But up here, where there was all this nitrous oxide, it was actually causing the steel to rust and the bolts to rust. Another good indication of PD. This is a situation I was telling you about where they have bus bars that were going, and they had this horizontal brace across the bus bars, and that horizontal brace was never cleaned. And it was in a swamp, in the Okefenokee swamp or whatever they've got out there. And it just had moisture and crap and dust, and that created a path that made the field strength between at the edges of this bus bar too great. And here's what happens. It just eats right into that insulation. This was screaming out ultrasonic. This you could hear with the naked ear. This was terrible. And it was on the verge of failure. This is from a full-time monitor system. And what they found within a few months of operation, that these cables, which are 35 kV, 34 kV cables up to PTs, are resting on these insulators. And this is what happens at that point where they're resting on the insulator. That's the burning that's starting from partial discharge. So what happened is, because you have this cable, there's no shield, and you have this sharp edge of the insulator, even though they're all insulators, it's still a geometric concentration of field, and that caused that discharge to occur. This, the switchgear manufacturer said this installation is fine. The customer high-potted it, and it was fine. They measured it, and it was fine. Within a month of energizing it, they had audible ultrasonic discharge, and you can see from this picture, within a few months, they had to replace all those cables and reroute them. This is a clear indication of where your typical installation looks okay, or the typical tests are all okay, but clearly this was going to fail in a pretty short period of time. And that's what unfortunately, this is a very super critical installation, and they put in full-time monitoring on every cabinet, and they found this long before it led to failure. Here's an example of internal discharge. So this was a rosin molded RFCT. The conductor has been removed from this channel, but they had this internal discharge from, this diagonal channel was cut into this hard plastic. Probably took decades to get there, but there was nothing to see. You could do all your normal tests. You could do a visual inspection. Nothing to see here until it failed. Unfortunately, we caught it just as it was on the verge of failure, and that was a manufacturing defect. So, and 20 years later, it failed. Again, more typical things, cable terminations. Once you peel that shield back, you can't get those cores that close together. Classic problem here, typical problems you see with trifurcated cables. This one's from a utility on an island in the Caribbean. They had a stack of switchgear laying in the corner. I took this picture. I could have taken a dozen more. This black tracing is treeing, tracking, classic surface discharge, the white powder being pulled out of the insulation, the copper turning green and white. That's all from the nitrous oxide. This is a mess, and this is basically just because they're in salt air, and there's nothing they can do about it other than to keep testing and changing it out. And I believe my last slide, so this is an overhead cable termination. This is internal and surface discharge. They had both going on, and they found it. We told the customer about it. I believe this was in Australia, and the customer did nothing about it. 5 months later, it failed. So, the customers may ask, well, how long do I have till it fails? That's the impossible question to answer. Maybe tomorrow, maybe, if it's real minor, you can give them, some sort of indication. But they want to know, how long can I run this before it fails? And that's not an answer we can always give them. Thank you for watching. And if you would like more information, or if you have any questions, please contact us at the information below.